Let's solve some exponential equations. We're going to start off with some that are pretty straightforward, pretty basic. Solve 2 to the x equal 8. The base here is 2. X is the power, or the exponent. And we're looking for the answer to be 8. So 2, when we raise it to what power, gives us 8. We know 2 to the 1 is 2. 2 to the 2, that's 2 times 2, that's 4. 2 cubed is 2 times 2, which is 4, times 2 more, that's 8. So that means our power must be 3. Solve 2 to the x equals 1 over 16. Well, the problem is this one has a fraction. 16 is in the denominator. There's a 1 in the numerator. So it might be helpful if we just ask ourselves this in maybe 2 pieces. 2 to the x equals, let's just look at the 16 first. What number do I raise 2 to get 16? Well, over here we saw that 2 cubed is 8. So now do 2 to the 4th. Well, that's going to be 2 times 2 times 2 times 2. This was 8. 8 times 2, this is 16. So we see that 2 to the 4th is 16. But my 16 is in the denominator. So that means x must be negative, a negative power, because we know that x to the negative n is the same as 1 over x to the n. If we have a negative exponent, it flips the position of the thing it operates on. So this is really like 2 to the x equals 16 to the negative 1. I could also think of this as 2 to the x equals 1 over 2 to the 4th. So looking at this in 2 different ways, 2 to the x equals 16 to the negative 1, or 2 to the x equals 1 over 2 to the 4th. So if I look at this one, 16 to the negative 1, we know we just said 16 was 2 to the 4th, so this is 2 to the 4th to the negative 1. The power is really negative 4. If I look at this one, 1 over 2 to the 4th, well, 2 to the 4th is in the denominator. So if I wanted it on top again, I would get 2 to the negative 4th. So then I look at x and negative 4 are both of the exponents. They have to be the same. X equals negative 4. Solve 4 to the x equals 8 to the x plus 1. If you noticed, the first two had common bases, right? This was 2 to the x, and this is really like 2 cubed. And this was 2 to the x and 2 to the negative 4. So can I get these in terms of the same base? Sure I can. 4 is 2 squared. And we know 8 is 2 cubed. So I'm going to rewrite that 4 and that 8 in terms of the base 2. So 4 to the x is 2 squared to the x. And 8 to the x plus 1 is 2 cubed to the x plus 1. We have some rules of exponents that tells us if we have a power raised to a power, we multiply. So 2 to the 2x is the new exponent. So we have 2 to the 2x on the left-hand side. Multiplying the exponents on the right-hand side, we get 2 to the 3 times x plus 1. So we have 2 to the 2x equals 2 to the 3x plus 3. Well, we see there's an equal sign here. We have an equation. Both of the bases are 2, so that means the powers must be the same. So 2x is the same as 3x plus 3. So I'm going to move this x over here. So 0 equals x plus 3. And I'm going to subtract 3 from both sides. So x is negative 3. Okay, let's try another one. Looking here, solve 4 to the x equals 7. Now, 4 and 7 are what we call relatively prime. They have no factors in common. So I'm not going to be able to use this process I used on the first 3, where I try to get them in terms of the same base. It's not going to happen. So I'm just going to have to try to solve for x a different way. The problem is x is in the exponent. How do I bring that exponent down to the regular equation level? Well, it'd be really easy if I had a logarithm, right? Because we know that if we have a log base b of some m to some power p, we can take that power p and rewrite it as the coefficient of a logarithm. So like p times log base b of m. Well, my x is in the exponent, right? So if I had a logarithm, I could move that exponent down to a coefficient. So that's easy. Just introduce a logarithm. we are going to take the log of both sides. You can pick any base you'd like. I'm going to use log base 10. So remember, if I just write log, that means log base 10. Now notice, I am not multiplying by log. I am applying an operator. So I have log. Well, my original problem was 4 to the x. So I'm doing an operator log of 4 to the x. And on this side, I had a 7. So I'm going to do log of 7. Now I have a log operating on something raised to a power. So this property here says I can just move that power in front of the logarithm like this. Okay, so I'm going to move this x in the front. So I'm going to get x times log 4 equals log 7. Now be very careful here. This is a product. This is x times log 4. Okay, now let's compare this to a problem we know how to solve. You may be thinking, I don't know what to do there. I don't like logs. I'm scared of them. So there's nothing to be scared of. Where it says easy, easy, easy. We're going to compare it to something we already know how to do. So what if I had something like x times 5 equals 19? I made this up. Has nothing to do with our problem. Well, usually we wouldn't write it that way, right? X times 5 equals 19. You'd probably see it like 5x equals 19. But mathematically, they are equivalent. There is a product. To solve this, either of these are the same thing, we would want the coefficient of x to be the number 1, right? So we would divide by 5 on both sides. Divide by 5 here as well. And then we'd get x is 19 over 5. So it's just some number times x. But that's what a log is, right? A log is just some number times x. So we're going to divide by that number on the left. But if we divide on the left, we better also divide on the right. So we end up with x equals log 7 over log 4. And you can type that into a calculator and get a decimal approximation. But this is a perfect answer. This is an exact answer. There is one other way to do this problem. Okay. We have a property that allows us to go back and forth between an exponential and a logarithm. We know that log base b of m equal n can be rewritten as b to the n equal m. The base of the logarithm and the base of the exponential are the same. We just switch the inputs and outputs, right? So start over here on this side. 4 to the x equals 7. And then switch the pieces. So that means we could have log base 4, because notice the base is the same of both of these. Okay, the input on the right-hand side is x, so that means it's going to be the output over here. The output on the right-hand side is 7, so that's going to be the input right here. So we could solve that. Most calculators won't do that. They will do log base 10 or log base e, so then we would use change of base. We would see that x equals log base 4 of 7 is the same as, pick whatever base you like. Most people like log base 10. Log base 10 of 7 over log base 10 of 4. You pick a base that you like, the same one on each. Lost a piece of my 4. And then 7 is above 4, so 7 is above 4. Do you see we get the same answer? Let's see if that's the right answer. Yep, there's our answer. Let's try another one. Solve 3 to the x minus 1 equals 5 to the x. This one is a little more complicated because there's x's on both pieces. But we're going to do the same thing. We're going to keep in mind that if we introduce a logarithm, we can move powers, exponents down, and they become coefficients of the logs. So recall log base b of m to some power p can be rewritten as p times log base b of m. You bring this power down to the front, and it becomes a coefficient. So we introduce a log of both sides. I'm going to use log base 10. You could also use log base e. You really could pick any log you wanted. But I'm going to do a log of the left and a log of the right. So the log operates on whatever is on the left-hand side, and it's also going to operate on the right-hand side. Now we can use that property that brings the powers down to the front. So we have x minus 1 times log 3. Log 3 is a number. And then x times log 5. Log 5 is a number. Now this one, like I said, is more complicated, so let's compare this to a problem we already know how to solve. So I'm just pulling a problem out of the air. Let's see. X minus 1, instead of log 3, I'm just going to make up a number. Call it 8 equals x times 7. Just made this up. It may bother you that the x minus 1 and the 8 are on different sides. Doesn't really matter. But if you were going to solve this in an algebra class, you may rewrite it like that. That's fine. What would you do first? Well, the first thing you would do is you would distribute right here, right? So you'd get 8x minus 8, and here you'd get 7x. So we're going to do the same thing. We're going to distribute. So remember, I could have also distributed like this, right? So we're going to look at log 3 times x and log 3 times the negative 1. If that bothers you to look at it like that, just rewrite it. Log 3 times x minus 1, if that's what you need to do. And I'll write this one the other way as well. Log 5 times x. So then we just distribute this times this. So we end up with log 3 times x minus log 3 equals log 5 times x. Now let's go back to the problem we know how to do. Over here we would get the x's on one side. So I'm just going to go ahead and move this. So minus 8x minus 8x. And then we get negative 8 equals, well, we'd have 7x minus 8x. Do not simplify it just for now. Okay, so I'm going to do the same thing here. I'm going to do minus this number. This is some number, log 3 times x, minus log 3 times x. We end up with negative log 3 equals log 5 times x minus log 3 times x. Okay, so let's go back to this problem we know how to do. Well, what would you do next? Probably you'd combine these values, right? You would do 7x minus 8x. And I'd love to do this in a class with a whole bunch of students, and they tell me the answer is negative x. But I say, wait a minute, not so fast. How did you get that? Well, you take the numbers 7 minus 8, so you get a negative 1, and then it's x. Most people don't say 7x minus 8x. In their mind, they do 7 minus 8. They're actually factoring out an x and subtracting the numbers. So that's the same thing we're going to do. Isn't that what you do? You don't do 7x minus 8x. You do 7 minus 8, and then you have the x. So you may even write more like this. Factor out the x. So 7 minus 8 times x. So we're going to do the same thing here. Notice they both have x's, right? There's an x here and an x here. So we're going to factor out that x. So we have negative log 3 equals x times log 5 minus log 3. So back over here, then we would divide by whatever that number is. As we know it's negative 1, but 7 minus 8 is the same thing, right? So here we're going to come through and we're going to divide by the number that's multiplied by x. Log 5 minus log 3. If we do it to the right-hand side, better also do it to the left-hand side. So we end up with x equals negative log 3 divided by log 5 minus log 3. Let's check our answer. Okay, now I want to point this out. Look carefully at the answer. Notice the answer we got is different than the answer that's posted. Look at the numerator. I have negative log 3, and what do they have? Positive log 3. Look at the denominator. Log 5 minus log 3. They have log 3 minus log 5. So what if I take my answer, negative log 3 over log 5 minus log 3, and what if I multiply by the number 1? I'm going to multiply by the number 1, but I'm going to pick a special number 1. What if I multiply the top by a negative 1, and I multiply the bottom by a negative 1? Well, I'd get a negative here and a negative here on top. That would give me a positive log 3. On the bottom, I'd have a negative log 5 plus log 3. And isn't this the same as this? The order's just backwards, right? So this is log 3 over log 3 minus log 5. Mathematically, these are equivalent because I multiplied by the number 1. Okay, wasn't that fun?